morning, students. My name is Vijay Kahar, Assistant Professor in Fire Technology Safety Engineering Department. Today, I would like to lecture the topic of heat transfer by conduction. Heat transfer methods, there are three modes of heat transfer: conduction, convection, and radiation. Starting the heat conduction, it is the transfer of heat from one body to another by means of physical contact. And second is the heat flow from the high temperature to low temperature. It's majority can in solid. मोस्टली जो देखा जाता है जो हीट ट्रांसफर कंडक्शन होता है वो सॉलिड के अंदर होता है एंड इट कैन आल्सो बी सीन इन लिक्विड गैसेस बट इज नेग्लिजिबल. Heat transfer. The details of heat transfer is form of energy. Heat transfer is energy due to the temperature difference. Heat travels from higher temperature region to lower temperature, and two bodies are thermal equilibrium when there is no net transfer of thermal energy. And for example of conduction, convection, and radiation. In thermal equilibrium, discuss about the thermal equilibrium. Heat always travels from a region of higher temperature to a region of lower temperature, the hot region to cold region. If two bodies are thermally in equilibrium, it means there is a temperature are not the same. When they are placed in contact, the thermal transfer occurs. Body A is at a higher temperature than body B. When body A and B are in contact, losses thermal energy at the rate of higher than the rate of at which it absorbs thermal energy from B. Here the A and B heat transfer from A to B. And this is another example of this causes the temperature drop in body A and increase in temperature in body B. Finally, the two bodies A and B have the same temperature. In equilibrium, heat transfer from A to B and heat transfer from B to A. They are in thermal equilibrium condition. Is the conduction. Conduction is the heat from the sources causing the atoms of the solid to vibrate and gain kinetic energy. Here is the same atoms are inert and vibrate increases. These atoms are cause neighboring atoms to vibrate. Kinetic energy transferred from the one atoms to the next. Molecular interaction. On taking the heat, the molecules remains stationary, but they vibrate in their lattice, which impart energy on neighboring particles in the direction of low temperature, and hence the condition takes place by drift or free electrons. In cases of metals, they have more free electrons which moves and collides with other electrons on supplying heat energy, thus causes the heat transfer. Conduction is the process by which is transmitted through a medium from one particle to another. This is an example of taking a rod, the metal's particles in the flame gains energy and so start to vibrate more vigorously, and the next middle part of the next particles are the pushed and pulled about there, the vigorously vibrating neighboring, so they start to vibrate faster too. And the end part of the rod, eventually the particles at the far end at the rod are made to vibrate vigorously. The end of the rod gets hot. Get the three rods of the same size. Here the example of get the three rods of same size. The rods are made of copper, iron and glasses. Rest then of tripod and fix the small nails at the end of the rod. Heat the other end of the rods equally with the booster burner. What happened? The nails from the different material drops off from the rod at different times. Here the taking three rods, copper, iron and glasses, and fix the nails held with the Vaseline. Materials and taken time from the pin drops. Copper time taken 14 seconds, iron 73 seconds, glass did not drop. From the experiment is so that the nails from the copper drop off at 14 seconds. This is because the heat travels faster through copper than iron and glass. We say that copper is good conductor of heat. For example of heat of conduction in manufacturing, heat exchanger, in industry, in electronics gadget, in motherboard of electronics, in everyday life, for cooking, and heating. Fourier law of heat conduction. This is a main important part of the Fourier law of conduction. Fourier law of conduction is empirical law based on observation and states as follows. The rate of flow of heat through a simple homogeneous solid is directly proportional to the area of the section at right angles to the direction of heat flow, and no change of temperature to respect to the length of the path of the heat flow. Mathematically, it can be represented by the equation Q is proportional to A into dt upon dx, where Q is equal to heat flow through a body per unit time. In the unit of heat flow in watt, it is denoted by capital W, and A is the surface area of heat flow. Is perpendicular to the direction of flow. The unit of area in meter square. dt is the temperature difference of the faces of block, homogeneous solid of the thickness dx through which heat flow in degrees Celsius and Kelvin. dx, thickness of the body in the direction of flow. The unit of thickness in meter. Thus Q is equal to, this equation is simplified, Q is equal to minus K into A dt upon dx. And K is the constant of proportionality and is known as thermal conductivity of the body. The minus sign of K is taken care of decreasing temperature along with the direction of increasing thickness of the direction of heat flow. The temperature gradient dt by dx is always negative along with x direction, and therefore the value of Q becomes positive. Assumption of the following assumption on the Fourier law is based. First, conduction of heat takes place under the steady state condition. Second, the heat flow is unidirectional. The next, the temperature gradient is constant and the temperature profile is linear. There is no internal heat generation. The boundary surfaces are isothermal in character. The material is homogeneous, isotropic. For example, the value of thermal conductivity is constant in all direction. Thermal conductivity. Thermal conductivity is denoted by capital K, is the intrinsic property of a material which rates its ability to contact heat. The thermal conductivity is defined as the quantity of heat Q transmitted through a unit thickness x in direction normal to a surface unit area A due to a unit temperature gradient dt under steady state condition, and when the heat transfer is dependent only on temperature gradient. The thermal conductivity of same materials at 20 degrees Celsius. Some example of silver is the maximum thermal conductivity of 407 watt per meter Kelvin. Same copper, aluminium, mild steel, lead, stainless steel, wood absorbs water and air. Here the values of thermal conductivity in unit of watt per meter Kelvin. Thermal resistance. Thermal resistance is denoted RTH when two physical systems are described by similar equation and have similar boundaries condition. These are said to be analogous. The heat transfer process might be compared by analogous with a flow of electricity in an electrical resistance. As flow of electrical current is electrical resistance is directly proportional to the potential difference dV. Similarly, heat flow Q is directly proportional to temperature difference dt, the driving force of the heat conduction through a media. As per Ohm's law, the electrical circuit theory, we have current I is equal to potential difference dV divided by electrical resistance R. The Ohm's law is equal to V is equal to IR. Then same equation is here, I is equal to V upon R. V is equal to potential difference. By analogy with the heat flow equation, Fourier's law might be written as heat flow. For the heat flow rate, Q is equal to temperature difference dt upon dx by Ka. By the comparing the equation 1.4 and 1.5, we find that I is analogous to Q and dV is analogous to dt and R is analogous to quantity dx upon Ka. The quantity dx upon Ka is called the thermal conduction resistance. The thermal resistance conduction is denoted by RTH conduction. The RTH conduction is the dx upon Ka. Here the figure 1.7 that show the temperature T1 to T2 and heat flow and mid resistance can be denoted RTH is equal to dx upon K. The reciprocal of the thermal resistance is called the thermal conductance. Types of state. Steady state. A system is said to be a steady state if its temperature does not change or vary with the time. An unsteady state. A system is said to be an unsteady state if its temperature changes with time. And next is the heat conduction through a plane wall. Case 1, uniform thermal conductivity. Refer to figure 2.4. Consider a plane wall of homogeneous material through which heat is flow only in x direction. Let L is the thickness of plane wall and A is the cross-sectional area of the wall and K is the thermal conductivity of the wall material and T1 and T2 the temperature maintained at the two faces 1 and 2 of the wall respectively. The general heat conduction equation is Cartesian coordinate. It given by del square T upon dx square plus del square T upon dy square plus del square T upon dz square plus qg by k is equal to 1 by alpha into dt upon tau t upon tau tau. If the heat conduction takes place under the condition steady state dt upon d tau is equal to 0, the dimensional d del square t upon del square y is equal to del square t upon del z equal to 0. So here the condition of del square t in y and z direction is 0 because the heat transfer only in the x direction and the no internal heat generation qg upon k is equal to 0. Then the above equation is del square t upon dx square equal to 0. Then simplify the equation is d square t upon dx equal to 0. By integrating the above differential twice we have, then the first time of differential is dt upon dx is equal to C1 and the second time differential here the dt upon dx to t is equal to C1 into x plus C2 where C1 and C2 are the arbitrary constant. The value of this constant might be calculated from the non-boundary condition as follows. At x equal to 0 and x equal to L. In a condition of x equal to 0, here the temperature T is equal to T1 and x equal to L, then the temperature is equal to T is equal to T2. Substituting the value in equation 2.34, we get T1 is equal to C0 into C2. The value of C1, the value of x equal to 0. The value of C1 is equal to 0. Then the C2 and the second condition is x equal to L and x equal to T equal to T2. So T is equal to T2 and C1 into x equal to L plus C2. After the simplifying we have C2 equal to T1 and C1 equal to T2 minus T1 upon L. Thus the equation 2.34 reduced to T is equal to T2 minus T1 upon L into x plus T1. This is the equation of 2.35. Then the equation of 2.35 indicates that temperature distribution across a wall is linear and independent of thermal conductivity. Now heat through a plane wall can be found by Fourier equation as follow. Q is equal to, and we taking the Fourier law of equation, Q is equal to minus K dt upon dx, where dt upon dx is the temperature gradient. But dt upon dx is equal to d by dx, a value of t. Value of t is T2 minus T1 upon L into x plus T1. So simplify the differential. T2 minus T1 upon L into x plus T1 is T2 minus T1 upon L. Therefore, Q is equal to minus Ka dt upon dx. Substitute the value of here dt upon dx. T2 minus T1 upon L. Then the minus sign is negligible. The K is equal to, here the simplify the T2 minus T1 is T1 minus T2. So minus sign is positive. The equation of 2.3.6 can be written as Q is equal to T1 minus T2 upon L upon K is equal to T1 minus T2 upon RTH. The value of L upon K is equal to thermal resistance of conductance, where RTH conductance, the thermal resistance of heat conduction from 2.4 be show the equivalent thermal circuit of heat flow through a plane wall. Let us now find out the condition when instead of space weight is means criteria of selection of the insulation of the plane wall. Thus resistance of conductance of the wall RT is equal to L upon K. Heat conduction through a composite wall. Before discussing about the heat conduction of plane wall, here the heat conduction through a composite wall. Refer to a figure 2.6a. Consider transmitted of heat through a composite wall consists of a number of slabs. Let LA, LB and LC thickness of slabs. Here the first figure 2.6 steady state condition through a composite wall. Here the three composite wall K, first A, B and C. Slab of A thermal conductivity Ka, and slab B thermal conductivity of Kb, and slab C is thermal conductivity of Kc. The length of LA, LB and LC. Here the temperature of T1, T2, T3 and T4. Interface temperature is T2 and T3. Initial temperature T1 and final temperature of T4. Here the circuit is thermal resistance of A, thermal resistance of B and thermal resistance of C. So thermal resistance of A is equal to LA upon K into A. A is the area of slab A. We describe here the LA, LB and LC, and T1, T2 and T1 is greater than always T4. The temperature at the wall of faces 1 and 4 respectively. T2 and T3 temperature at the surfaces 2 and 3 respectively. Since the quantity of heat transmitted per unit time through each slab is same, we have Q is equal to Fourier law of heat conduction formula here. So K is equal to A into T1 minus T2 for the first slab divided by length of first slab LA, and here second is the slab 2 Kb into A, T2 minus T3 upon LB, and slab C is the Kc into A, T3 minus T4, the temperature difference of T3 minus T4 for slab C divided by LC, length of LC. Assuming there is a perfect contact between the layers and no temperature drop occur across the interface between the material. We have discussed above before. Rearranging the above expression, we have T1 minus T2. Here the mistake here, T1 minus T2 first. So Q is equal to L upon K into A, slab 1. And T2 minus T3 second. Q is equal to LB upon KB into A. And third is the T3 minus T4. Q upon LC upon Kc into A. Adding the equation first, second and third we have, and cancel the here T2 and T2 and T3 and T3 cancel. The final is T1 minus T4 is equal to Q and bracket LA upon K into A plus LB upon KB into A plus LC Kc into A. Q is common. So Q is equal to, simplify this equation, Q is equal to A upon T1 minus T4 upon L upon K plus LB upon Kc and LC upon Kc. Of Q is equal to T1 minus T2. A is divided to the LA upon K into A. Then same LB upon KB into A, LC upon Kc into A. So T1 minus T2. So this the phenomenon of LA upon K into A is the thermal resistance of A, and thermal resistance of slab B and thermal resistance of slab C. If the composite wall consists of n slabs of layer, then final equation is Q is equal to T1 minus T n plus 1 upon sigma L upon K. Numerical example of conduction. A plane wall of 150 mm thick and its wall area is 4.5 meter square. If its conductivity is 9.35 watt per meter degree Celsius and surface temperature is steady at 150 and 45 degrees Celsius. Determine heat flow across the plane wall. And second, the temperature gradient in the flow direction. So first we calculate the heat flow across the plane wall. So we have given that the thickness of the plane wall L is equal to 150 millimeter. So then can you convert into unit in meter? 0.15 meter. Area of the wall A is equal to 4.5 meter square. Temperature difference dt is equal to T2 minus T1. T2 is the 45 degrees Celsius and T1 is the 150. And the finally minus 105 degrees Celsius. Thermal conductivity of the wall material given K is equal to 9.35 watt per meter degree Celsius. So first we calculate the heat flow across the plane wall Q as Fourier's law. Q is equal to minus K dt upon dx. The substituting the value here and final Q is equal to 29,452.5 watt and temperature gradient. The part of the Fourier's law dt upon dx is the temperature gradient. The Fourier's law we have dt upon dx equation is equal to dt upon dx is equal to q minus upon k. Substituting the value of q and k and a. The final result we have find minus 700 degrees Celsius per meter. We just simplify the discuss about the convection. Convection is the transfer of heat from one place to another due to the movement of fluid. Here the movement of fluid, there are two types of convection, forced convection and natural convection. For convection with the help of any types of fan to convert the heat transfer and natural convection naturally. The rate of equation of the convection heat transfer between a surface and adjacent fluid is prescribed by the Newton's law of cooling. We have find about in the conduction, so we have the Fourier's law and convection is the Newton's law. Q is equal to HA Ts minus Tf, where Q is the rate of heat transfer in watt, H is the transfer of coefficient, the unit of heat transfer coefficient watt per meter square Kelvin. A is the area of heat transfer in meter square. Ts is the surface temperature in degree Celsius or Kelvin. Tf is the fluid temperature degree Celsius or Kelvin. Radiation. Thermal radiation is the transfer of heat in the form of radiant energy or wave motion from one body to another across an intervening space. And here the example of cold time, sun heat the earth by the electromagnetic waves, hot bodies emitted heat waves. Stephen-Boltzmann law. Stephen-Boltzmann law is also called the Stephen-Fourth power law and emissivity. Rate of heat transfer Q dq upon dt is proportional to area and same is the fourth power of temperature. So for the perfect body, black body is dq upon dt is equal to sigma a t to the power 4. For any other body, dq upon dt is equal to epsilon sigma a t to the power 4, where E is equal to emissivity. The value of emissivity is 0 to 1, between 0 to 1. And sigma is Stephen-Boltzmann constant. The constant value of 5.672 into 10 to the power minus 8. The unit of constant value of sigma Stephen-Boltzmann constant is joule per meter square second k to the power 4. A is the area of heat transfer in meter square and T is the temperature of the body in degree Celsius or Kelvin. Thank you very much.